We already saw that in the previous classes when we discussed stability of infinite slopes. I guess you guys are familiar with the term stability number. What is stability number? C by gamma z or hc. Okay, right. It's a dimensionless parameter, which is a function of uh, different soil parameters or slope parameters, right? So we saw ZC from the basic expression of stability number. The basic expression of stability number that we saw previously was Sn is equal to C by gamma ZC, right? So we know that if you rearrange it, you can see that ZC is equal to C by gamma Sn. We know that ZC is proportional to C and ZC is inversely proportional to gamma. What is this ZC? What is this ZC? Depth at which the soil is at equilibrium, that is ZC, the critical depth, right? So anything above that, if the slope is unsupported, then your slope is going to fail, right? So ZC, we know that it's a function of it's proportional to the cohesion of the soil. The higher the cohesion of the soil, more can be your critical depth, right? Isn't it? So if it is a cohesive soil, the soil can stand on its own, and you can, you have unbraced cuts or unsupported excavations, isn't it? So ZC is proportional to cohesion of the soil. We know that ZC is inversely proportional to density of the soil. We see that, right? We can see that ZC is inversely proportional to density of the soil. The more dense the soil, more will be the weight of the wedge, and it has higher probability of sliding down. And we have also seen that ZC is a function of phi and I in the previous derivations, right? And the derivations for infinite slopes, we saw that this ZC is dependent upon phi and I also of the soil, right? So we can say that ZC is equal to C by gamma into Sn, where that Sn is a constant or dimensionless parameter, right? ZC is equal to C by gamma, right? It's proportional to C, it's inversely proportional to gamma. So ZC is equal to C by gamma Sn, and Sn is equal to C by gamma ZC. We saw this, isn't it? It's just a revision of what we already saw. All right. And for the soil, when this, so in the soil, when the cohesion is just mobilizing at ZC, it can be Cm also, right? Because at ZC it's at equilibrium. That means the whole cohesion of the soil is mobilized. So C will be equal to Cm, right? And factor of safety will be equal to 1 at equilibrium. So I can also say that Sn is equal to C. In terms of Cm, I can say that Sn is equal to Cm by gamma ZC. And we equated this and we derived the expression for factor of safety in terms of cohesion. So this also we saw, or everything on this slide, on the left side of this slide, we have already seen. Okay, everything on this side we have already seen. Okay, this is nothing new. All right, so we can see that the expression of stability number, the main parameter here, it is C itself, right? So if it is a cohesionless soil, purely cohesionless soil, then your C is going to be 0, and your stability number depends only on the slope's angle. Okay, and Taylor's method is invalid because we are not going to use this dimensionless parameter stability number for any of the further calculations. The slope stability depends only on the slope angle I, isn't it? Can you correlate and visualize it? If C is equal to 0, that means there is no cohesion for the particles to be held together. All right, you are trying to visualize a sandy slope, right? So stability of that slope depends only on the slope angle, isn't it? The steeper the slope, the more unstable the slope is going to be, right? So that slope stability is going to depend on I alone. So I'll come to where we are going to see this further. So just keep this in mind. And we also saw the basic expression for factor of safety. It was tau f by tau, right? We saw this in the second class of slope stability, right? So factor of safety is equal to tau f by tau, and also I can say that tau is equal to tau f by f, and that tau, here you can see that tau is equal to shear strength. Shear stress in the soil will be equal to shear strength of the soil divided by factor of safety. Shear strength of the soil, basic equation C plus sigma tan phi. So divided by F, that is C by F plus sigma into tan phi by F, right? Again, I know the factor of safety in terms of mobilized cohesion, so I am just representing that here again. Okay, Cm is equal to C by F. Okay, I'm just refreshing all these expressions that we have seen previously, because we will be using these for the problems that we are going to do now. Now we will come to this bottom left. We will come to this. Okay, let's see here now. So here we can see two charts that is dependent upon the stability number. You can see on the left you have the stability number. So what is the stability number? It's a dimensionless parameter which is dependent upon the cohesion mobilized and density of the soil and the depth of excavation, right? Depth of the slope, h. Okay, instead of z here I have used h. Okay, then here you have the slope angle. All right, so this is a chart for C5 soils, so that represents the stability numbers for C5 soils. Okay, these lines represent phi of the soil. All right, and this Sn is a function of C of the soil. Okay, and this is my slope angle. Okay, I'll tell you where we are going to use this. All right, so this is a chart for C5 soil, and this is a chart for C soil where phi is equal to 0. Okay, so this chart basically depends upon the depth factor and the stability number, and these lines here you can see different angles written here. So all these lines represent different slope angles. Okay, here this is basically dependent upon the depth factor. Okay, so depth factor is a new term I'm going to introduce to you now. So depth factor, I've written it here, df is equal to d by h. Okay, and this is my h and df is my depth factor. All right, so df is equal to d by h. df is equal to d by h. So this we assume, and that d is the depth of hard surface from the top of the slope. Okay, d is the depth of hard surface from the top of the slope. Okay, so df is equal to d by h is the relationship. Okay, just keep these things in mind. I'll come to how and when we are going to use this. So if it is a purely cohesive soil, then we have to take into consideration this depth factor df, where df is equal to d by h. Okay, so if we have a hard strata underneath a soil like this, then you have a stronger soil beneath and you have a weaker soil above. So there is a chance for base failure, right? Correct? We saw this. Yeah, the slope angle is I, and the uh, the critical failure surface is going to intersect some point in front of the toe at a distance n into h. Okay, n times this h. Okay, assuming that the critical failure surface touches some point after the toe. Okay, and that distance from the toe is n times h. Okay, and another parameter is depth factor df, where df is equal to d by h. Okay, keep this in mind, and this we are going to use here, this depth factor here. All right, here I have the depth factor, and here I have these dotted lines which represents the n. Okay, what is n? This is n. Okay, n times h. So what is the value of that n? All right. Okay, so the C5 soil chart, it's based on the assumption that the critical failure surface passed through the toe. Okay, this charts. So this is based on the assumption that the critical failure surface passed through the toe or above the toe. Okay, and this for purely cohesive soils, it is assumed that the critical failure surface pass at some point above the toe or at the toe or some place above the toe, where you find this factor n and this factor df. Okay, and based on this, for purely cohesive soils, you can find out your stability number. Okay, all right. But in the other case, if it's a C5 soil, you assume that the slope fails above the toe and pass through the toe or above it. So you can take the basic equation for shear stress in soil. So S is equal to, we saw this relation just before here. So S is equal to C by F plus sigma into tan phi by F. So in terms of factor of safety, in terms of cohesion, we saw Fc is equal to C by Cm. Similarly, hereafter we are going here for this condition, we are going to consider factor of safety in terms of angle of internal friction of the soil. All right. So phi m, which is my mobilized friction, will be equal to, that is tan phi m will be equal to tan phi by f, right? So phi m is equal to tan inverse of tan phi by f. So phi m is equal to phi by f, right? So that is my factor of safety in terms of mobilized friction. Okay. So if you are considering C5 soil, you have to assume, you have to consider this phi, these phi you have to consider your mobilized friction. Okay, so for that mobilized friction and for the given slope angle or for the given C, what is your slope stability number or your slope angle? These values we are going to use for further calculations. Okay, so this chart gives you a relationship between all these soil parameters and slope parameters and lets you figure out various parameters from these charts like SN, I, and phi. So once you have any of these, if you don't have any of these parameters, you can, once you have this chart, you can find out any of these parameters by back calculation, right? If you want to find Cm, if you have phi and I of the slope, you can find the C of the slope, right? Similarly, you can do any sort of back calculations and figure out those parameters. All right. Now, for phi soils, I is less than or equal to 53 degrees. You assume that the critical failure surface extends below the toe, as I showed you the previous figure. If it is a purely uh, uh, cohesionless soil, right? So, sorry, purely cohesive soil. So, in that case, you use a depth factor, right? So there you assume your depth factor, and you assume that the phi is completely mobilized. So the f phi that I explained earlier, that is going to be equal to 1, right? Because phi is equal to phi m. So f phi is equal to phi m by phi, which is equal to 1. And depending upon that depth factor and slope, the critical failure surface will pass through the toe of the slope or at a distance nh in front of the toe, as I showed you in that figure. All right. So let's just do a problem. I'm sure that you guys are still wondering what these are and why we are discussing this or what you are going to use these for. So let's just do a problem, and then I think you will understand how to make use of this. And let me come back to this bottom left. You can see if phi is equal to 0 and I is equal to 90 degree, all right, phi is equal to 0. It's a purely cohesive soil. Only C is there. So if the slope is having a cut angle surface of 90 degree, I mean slope angle of 90 degree, that means it's a vertical cut, right? So if your soil is purely cohesive, that is clay soil, and if your cut is 90 degree, that's a vertical cut, then phi is equal to 0. So here you can see my slope angle is 90 degree. It's a vertical cut, right? Slope angle is 90 degree and phi is 0, purely cohesive soil. All right. If phi is 0, then my stability number at this point 90 degrees and phi is equal to 0. My stability number is 0.26, right? Stability number, it is 0.26, right? So in that case, Sn is equal to 0.26. So what will be my critical height? So Zc will be equal to C by gamma Sn, which will be equal to C by that Sn is 0.26. So it will be equal to some, 0.01 by 0.26, roughly equal to 4. So your Zc is going to be equal to 4C by gamma. Right? We saw another equation earlier for HC in the case of tension cracks. Right? Similarly, here my the depth up to which my slope is going to be stable without any support is going to be 4C by gamma. So you can see that it is a function of cohesion and inversely proportional to density of the soil. Right. So keeping these things in mind, don't worry. I'm pretty sure that you guys are still, a bit confused. So let's do one or two problems, and you will know how to use these charts. Take down the problem. Take down the problem. So you can see that it is a C5 soil, isn't it? Right? You have the C parameter, you have the phi parameter. So obviously it is a C5 soil. So which chart are you going to use? This one, isn't it? It's a C5 soil. So using this chart, I want you to find out the mobilized cohesion. So you can see here there is a parameter for mobilized cohesion, isn't it? So I want you to find out the mobilized cohesion, and using the mobilized cohesion, you can easily find out your FC, right? Factor of safety with respect to cohesion, isn't it? And based on that, you can identify whether your slope is stable or not, right? So that is the basic purpose of this. You can identify the slope stability, you can identify the factor of safety against slope failure, right? Is the question clear? So I have my phi is equal to 15 degrees. So you can see 15 degrees here. this line. So this is the line I am going to adopt, right? So phi is equal to 15 degrees. And what is my I? What is my I? Slope angle 37 degrees, isn't it? So this is 30 degrees, this is 40, this is 35. So somewhere here. So somewhere here. So what is the value of my stability number? 0.07. So now you have your stability number value. So that value will be equal to what? Your Cm by gamma h, right? Can you find out your Cm? 18.9 unit. So how much is my factor of safety here? Because out of the maximum cohesion of 200, only 18.9 has been mobilized yet, isn't it? So you can definitely have a much steeper slope there, right? Now can you correlate that idea now? How the Cm and slope stability is correlated? Can you imagine now mobilized cohesion? I hope so, because you can see that the soil has a cohesion of 200 kilonewton per meter square, but at this slope angle, only the cohesion of 18.9 has been mobilized yet, isn't it? The stresses developed has mobilized only 18.9 kilonewton per meter square. So, you can go much steeper for that slope, isn't it? So this is where we basically use stability number for all types of slope stability analysis. Like, if you have the slope angle parameters of the soil and density of the soil, you can find out, basically you can find out whether your slope is stable or not from these charts very easily. Right? It's like a simple readout. You have only one or two equations and you can simply, you can use it like a readout. Okay. Next question. Take down the question. Okay. First thing, draw a rough figure and figure out your depth factor. If you need to draw a rough figure, you can draw that. How much is my depth factor here? What is the equation for depth factor? df is equal to, so what is the d here? 20 meters, right? And h is 10 meter, yeah, cut 10 meter deep. So how much is my df? 2, correct. And what is my I? 30 degrees, correct. So now let us look at this graph. So everyone have df is equal to 2 and I is equal to 30 degrees. Now let us look at this graph. Okay, so this lines represent my I. Okay, so this I is 30 degrees here, right? I is 30 degree, then my depth factor is 2, right? So for 2 and 30 degrees, can you find out my stability number? Exact value is 0.172 for your information. Okay, exact value is 0.172. So now what do you have to find out? I have asked you to find out whether the slope is stable for a factor of safety with respect to cohesion 1.5. So now what do you have to find out? You have the stability number now, and I want you to find out whether the slope is stable with the factor of safety with respect to cohesion 1.5. Okay, so what will you find out next? Cm, yes. So I have the expression Sn is equal to Cm by gamma h. So from that I can easily find out my Cm, right? So how much is that? 30.96. And what is the maximum cohesion this soil can have? What is the cohesion of this soil? 27, right? So is that possible? What is the factor of safety with respect to cohesion here? 0.872. So that is less than 1, isn't it? It is not even near 1.5. It is even less than 1. So definitely it's not stable, right? So hence it is not safe. So now what you have to find is, first part of the question is over. Determine from Taylor's charts if a 30-degree slope is safe or not. Is it safe? No. Now we have to find out, for a factor of safety of 1.5, what is the safe angle of slope, right? So for that, what will you do? Now you have to back calculate, right? Factor of safety with respect to cohesion is given as 1.5. Now you have to find out, for a factor of safety of 1.5, how much cohesion should be mobilized, isn't it? So now you have to back calculate your Cm. How much is your Cm? 18, correct. So for 18, for a CN of 8, a CM of 18, how much will be your SN? 0.1, right? So here, where is 0.1? This is 0.1, right? This is the line for 0.1, right? And what is my depth factor here? So for a depth factor of 2 and a stability number of 0.1, what will be the slope angle? 7.5. Its exact answer is 7 degrees. Okay, so something around 7 degrees, 7.5. All right, right? 7 degrees. So you can say that from this chart and from the back calculation, you have found out that for a minimum factor of safety of 1.5, your slope should be 7.5 degrees inclined to the horizontal, right? So you can figure out different aspects of slope stability directly as a readout from this Taylor's stability charts. So is the usage of Taylor's stability charts clear now? Hope it is clear. Next question. Have you taken down the question? So we'll use this figure because it's a C5 soil. The C is 30 and phi is 20 degrees, so it's a C5 soil. So we are going to use this figure. 0.03 is the exact value. Right. So now for that, what is your CM? 14.58. So what is the C of the soil? 30. Yeah. So is the slope safe? It is safe. But what you just found out is the factor of safety with respect to cohesion, right? But this is a C5 soil. So the phi also will try to resist the soil slope failure, isn't it? So in this C5 soil, both the C and phi will resist the soil. So you have to find out the mobilized phi here, correct? You have to find out how much of the angle of internal friction of the soil is mobilized right now, right? So for that, you have to assume now you have a factor of safety with respect to cohesion, you have a stability number, etc. Now, for the uh, now you have to assume a factor of safety with respect to phi. Okay, with respect to phi alone, you assume a factor of safety of 1.5. Okay, let us start with 1.5. Okay, and you have to find out your mobilized phi, and from the graph you have to come back to the graph and find out your SN again. Then for that SN, you calculate your CM once again. And for that CM, you have to see whether your FC and your F5 are matching. If it matches, your slope is going to be safe. Or maybe sometimes the cohesion fails and sometimes the phi fails, right? So now you assume, earlier we saw that for the given conditions, my slope is safe with respect to cohesion, right? Now, assuming a factor of safety of 1.5, factor of safety with respect to internal friction, F5, assume 1.5, and for that you find out how much of the cohesion is, how much of the friction is mobilized. How much is your phi m? For F5 is 1.5. 1.5 is equal to 20 by phi m. So phi m will be equal to 20 by 1.5. How much? 13.33. Now for that phi m, somewhere here, for that phi m, you find out your SN. For that phi m, you find out your SN. How much will be that? 0.07. Now for that SN, you back calculate your CM. Right? Back calculate and find out your CM and see if your slope is safe with respect to cohesion for that mobilized friction. .02. So how much is your factor of safety with respect to cohesion? And how much was your factor of safety with respect to angle of internal friction? 1.5. No, that is what you assumed, right? But your factor of safety with respect to cohesion is less than 1. The slope safe? No. So now you have to assume another value of factor of safety, and see whether your factor of safeties are almost similar. Okay, if it is so, then we can satisfy the basic we saw earlier. This one, see here, this is the condition we are trying to satisfy. All right, here's the condition we are trying to satisfy. Or here, see here, right? So your factor of safeties with respect to both should almost match. Then you can say that your slope is stable. So now you have to do a trial and error. You have to assume different values of factor of safety with respect to angle of internal friction, and back calculate the factor of safety with respect to cohesion, and find out a value which which is compatible with both. So that factor of safety, you can say that your slope will be that parameters for that slope will be safe. So I want you to do that as a homework today, and we will see how much is that value in tomorrow's class. All right. Thank you.